DNA. Look, listen, and learn. So let us see how the DNA is packed inside our cell in the topic called as packaging of DNA. Okay? Now, let us consider a double-stranded DNA molecule. I'm going to call it as dsDNA. Look at this molecule of DNA. Whoa, what do you see? That's a DNA molecule and it's double-stranded. Can you measure the length of this DNA molecule? Yes, you can. Let's go ahead and measure. Wait, it's not done yet. Why? Because this DNA molecule is still longer than you think. Now can you measure? Yes, you can. Go ahead. Wait, it's still not done because this DNA molecule is still longer. There you go. Now we have a complete DNA molecule. Is that okay? And if you want to measure the length of this molecule measures about 2.2 meters in length. Where do you think this molecule is present in the eukaryotic cell? We know that area highlighted. And what is that area? You guessed it right. It is the nucleus. Right? This nucleus also has a diameter. And what is the diameter of the nucleus? It is roughly about 10 minus 6 of a meter. Is that okay? Now if I ask you to fit that 2.2 meter long DNA in this small nucleus, can you fit it? I don't think so. So what do you think you should do to that DNA? Let us see. Okay? So that DNA, which is 2.2 meters long, has to be condensed to fit inside the nucleus. So let's go ahead and condense it. There you go. Now can you fit the DNA in the nucleus? I don't think so. Not yet. So what is my next step? I'm going to coil it. So let's go ahead and coil this DNA. We did. And now I'm going to condense it some more. Now can I fit in the nucleus? Kind of maybe. But still not correctly. So what else can I do to it? I'm going to super coil it. You see that? Now I have super coiled my DNA. Right? So I have taken my DNA, which is 2.2 meters long, I have condensed, I have coiled, I have super coiled. And now do you think this DNA will fit inside that nucleus? Yes, absolutely. See how it fits? Right? So for the DNA that is too long to fit inside that small nucleus, it has to be condensed, it has to be coiled, and also has to be super coiled. Only then it can fit inside that nucleus. Is that okay? Now, in eukaryotes, organization or packaging of DNA is rather complex. It is not as easy as you just saw up there. So let us see how this really happens. Okay? Moving on. Eukaryotes. In eukaryotes, you require special proteins for packaging of DNA. And these special proteins are called as histone proteins. Is it okay? So what is this histone protein? Let us see. Now, histones are basically proteins that are rich in positively charged basic amino acids like lysine and arginine. Okay? How many histones do we have? In eukaryotes, there are about 5 different types of histone proteins. Let us see what are these 5 histone proteins. They go by the name of H1, okay? Then there is an H2A, okay? Then there is an H2B, right? Then there is H3, and finally there is an H4. So you see there are 5 different types of histone proteins: H1, H2A, H2B, H3, and H4. Is that okay? Now, let us see how can we use these histone proteins to pack or wrap our DNA. Fine. Listen carefully. For the packaging of DNA, you require a histone octamer. An octamer basically is histone proteins in a group of 8. Let us see how would we make an octamer of histone proteins. For making an octamer, you will require 2 molecules of H2A. You'll require 2 molecules of H2B. You'll require 2 molecules of H3, and you'll require 2 molecules of H4. So 2 molecules each of H2A, H2B, H3, and H4 will make a histone octamer. Is that okay? Now the DNA has to wrap itself around this octamer, and let us see how it wraps. Look carefully and observe. That is your DNA. Okay, I'm representing the DNA double helix as this yellow structure. See how it is wrapping around the histone? It is just turning around the histone. And how much turn do you think it takes? You must know that DNA takes about 1 3/4 turn around the histone octamer. And what you see here coiled around the histone octamer is nothing but the double-stranded DNA molecule. Is that okay? Now here you go. There's H1. It kind of finishes that packing and touches on the outside, so the DNA is fixed onto the histone octamer. Is that okay? What you see here is a negatively charged DNA molecule which is wrapped around the histone octamer, which was positively charged, and this structure together is called nothing but a nucleosome. So if they ask you what is a nucleosome, you can simply say a negatively charged double-stranded DNA, right, around the positively charged histone octamer is called as a nucleosome. And how much turn the DNA takes? Please remember, the DNA takes about 1 3/4 turn around the histone octamer to form this structure, which is called as the nucleosome. Okay? Now, this module, we finished the first part of packaging of DNA. In the next module, we're going to begin with the second part of the packaging of DNA. Thank you and take care.